Hi, this is Alex from devstories.eu. OpenCV Computer Vision Deep Dive, Episode 13 of 20. We have spent years training AI to draw bounding boxes around objects, but boxes are clunky and full of background noise. The real goal is asking a system in plain English to paint a pixel-perfect silhouette around the exact contours of an object, even if it has never explicitly trained on that object before. That brings us to vision language models for segmentation. Traditional image segmentation models are rigid. They map pixels to a fixed, closed list of categories like car, person, or tree. If you want to segment something outside that list, you have to collect a massive data set and train an entirely new model. Vision language models, or VLMs, break this limitation by fusing large language models with visual encoders to perform open-world segmentation. You input an image and an arbitrary text string, and the model returns a dense pixel-level mask of whatever you described. Consider an automated agriculture drone flying over a vineyard. A farmer does not want generic boxes around plants. They need a precise map of infection. They prompt the drone with the text string, diseased grape leaves. The VLM processes the visual feed and the text prompt together. It understands the semantic meaning of diseased and grape leaves from its language training, aligns that meaning with the visual features of the image, and outputs a mask. This mask isolates only the infected foliage down to the exact pixel, completely ignoring healthy leaves, soil, and shadows. This brings us to how the model actually executes this logic. The baseline approach is zero prediction text prompting, often referred to as zero shot. In this mode, the model relies entirely on the vast dataset it was originally trained on. The text prompt passes through a text encoder, turning into a mathematical representation of your request. Simultaneously, the image passes through a vision encoder, breaking the picture into a grid of visual features. The model then computes the similarity between your text representation and every single visual feature in that grid. High similarity scores become your mask. The crucial point here is that the model weights remain completely frozen. You are extracting a complex pixel mask using only the power of language alignment. Here is the key insight. Zero prediction is powerful, but it relies on broad, general-purpose training. Sometimes the visual domain is simply too specialized. If a specific grape leaf disease looks identical to a harmless nutrient deficiency, the frozen VLM might struggle to differentiate them purely from a text description. This is when you switch to visual fine-tuning. Instead of just changing the text prompt, you update the actual weights of the model's visual components using a small dataset of highly specific, manually masked images. You are explicitly teaching the vision encoder the nuanced visual texture of the disease, rather than just relying on the language model's broad conceptual understanding of the word disease. Zero prediction treats the VLM as an out-of-the-box reasoning engine, steered entirely by words, while visual fine-tuning treats it as a powerful foundation that you permanently alter to master a specific visual domain. That's all for this one. Thanks for listening and keep building.